how to randomize to optimize. And let me just share the slides. I think we should all see that. If anything's off with the sound or the video, just send a message in the chat and I'll see it. You should be good.
Okay. Hello, everyone, and it's great to be in Seattle again for, Seattle has been for a long time my home, and I left about 3 years ago, and this is the first time that I've returned, and it's nice to see nothing's changed. The weather in San Diego right now is quite sunny, in case you were wondering. So thank you, Tom, for inviting me to give kind of a soft introduction to the conference. I have tried to gather in my talk a lot of the themes and threads that will be present throughout this 5 days of talks. You will see me mention at some point names of other people who are here or who may come here and who will talk about their work. This is because it's a mini course. It's more of a survey with kind of certain themes weaved in. And the beginning is going to be kind of soft, and toward the second part of the mini course. It's hard to say it that way because it's essentially one very long talk split into 4 parts. But that's when we're going to see some more meaty stuff. But for now, it's going to be, as I will show you in a moment, introductory stuff, history, and generalities. So, okay. So, what is this all about? For several decades now, there has been a very interesting and deep intertwining of randomness and numerical linear algebra. In many ways, random matrices have come to play a relatively major role. Maybe I should take out relatively, a major role in the last decade and a half or two, with the advent of all sorts of new tools and methods for both doing modern, let's say, numerical linear algebra, but also for applications in other fields, from data mining to data science to machine learning to neural networks. And so this is all fairly new still. It's very happening. Some of the people who are scheduled to speak, but maybe are not quite here yet, have played a role since the inception of this field, and have helped put the foundations down and kind of like define it and set out some principles for working within it. And I'm talking about Mike Mahoney. And basically, like I said, what I'm doing here is just to offer you an introduction in this. So the following is the contents of this first part of the mini course. So it'll be now about 30 to 35 minutes of lecture, followed by 5 minutes of break, followed by another 40 minutes of lecture. In the first part, I intend to cover these first 3 bullet points. And in the second part, I'll talk about the other 2. So the first part of the talk is going to be history, motivation, and basics. So let's talk about the history of the field. Well, like I said, it's a fairly new field, but of course, like everything in applied math, everything is fairly new. We're talking about things that have happened in the last 80 years or so. We don't have the kind of history that certain subfields of algebra or geometry or number theory have behind them. So whatever I say is going to be fairly new, but the use of randomization in numerical analysis has been around for about 80 years now, which is pretty old in our field, starting with, of course, the work of Ulam and von Neumann on Markov chain multi-parallel methods. So that would probably be the advent, let's say, of this entire subfield. But pretty quickly, people have caught on to the fact that if one introduces a little bit of randomization to understand the mechanics, the underlying mechanics of a numerical procedure, you can do better on the one hand and gain some understanding of the theory behind it as well. So pretty soon afterwards, well, okay, not that soon maybe, but with the work of Dixon in the 80s and two Polish mathematicians, Kuczynski and Wozniakowski, in 93, they introduced this idea of the power method, using the power method or the Lanczos algorithm with random starts, with random input vectors, and it was shown to converge. The first, real result for convergence of these methods on random inputs. And then things really took off. So in the late 80s and early 2000s, there was a plethora, not a plethora, sorry, I've been told that plethora has a slightly negative connotation. I should use bevy instead. There was a bevy of work, mostly coming from theoretical computer science, optimization, and the incipient machine learning, that took these ideas and started to implement them in a powerful way. So this idea of sampling columns of a matrix to better understand what its rank might be, or its range for that matter, really started out with the work on random embeddings of Noga alone, of course, Gibers, Matias, and Szegedi in 2002. And then it was pursued with, well, actually, this was slightly before that, but the random embeddings is a little bit, actually, I should have reversed this too. It's a more refined version of low rank approximation. The work of Papa Dumitriu, Ragavan, Tamaki, and then Pala really started off this idea of sampling columns of a matrix for understanding its rank and its range. And here is where things stopped being a one-off. You know how it is, because you start using a certain type of tool in a new field, and people think, well, that's a nice trick, but will it survive? Will it build? Will it grow? And it's not necessarily true all the time. Sometimes it's just a nice trick that leads nowhere, and sometimes it's really something that starts building a new field. And that's when things really started getting onto a path of development.
This meeting is being recorded.
Truly a new field, and this involved the theoretical principles around randomized numerical linear algebra that were set out by Drenies, Cannon, and Mahoney in a series of papers starting in 2006. And then another bevy of methods for low rank approximation were introduced kind of like in short. It was a burst of research activity that originated on the East Coast at Yale and NYU with the work of P.G. Martinson, Vladimir Rochlin, Mark Teigert, and also continued by Liberty, Wolf, Martinson, Rochlin, and Teigert in 2006 and 2007. And they came up with a lot of the algorithms that I will be talking about or alluding to today, including analysis. I think that this last paper, 2007, was published in the Proceedings of the National Academy of Sciences. And by 2011, there was so much going on that surveys started being published. So Mike Mahoney's survey was probably the first one of the field, but then it was shortly followed thereafter by what I like to think of as a seminal foundational work of bringing all of these things together by Nathan Halko, P.G. Martinson, and Joel Trop. This is a huge paper that has served as a reference for me for years for this sort of research. Then Joel Trop published another survey of concentration inequalities that are of use in numerical linear algebra in 2015. And just 3 years ago, P.G. Martinson and Joel Schwab again came out with another huge survey, this time of the entire field, including not just low rank approximation and range finders, but Lanchos methods, Krylov spaces, and notably the one method or the one concept that has exploded since 2019, which is stochastic gradient descent. So, so this is kind of like this latest state of the art, let's say, but who knows if next year something else will come up and we'll have more to say about it. Okay, so like I mentioned, essentially one of the most influential ideas out there in this random use or use of randomness in numerical linear algebra has been the introduction of stochastic gradient descent. And we're going to hear about that, a lot about that in the next two talks that follow mine. Okay, so let me put this into perspective. I have looked through the list of speakers and I've identified a whole bunch of talks that will have a lot to do with what I've been mentioning here. And these are, you know, apologies. These are just some of them. If you're also giving a talk and it's relevant to what I said, I apologize for mixing you. It was not a deliberate attempt. So it's not an inclusive list. So let's see. So when it comes to low rank approximation, projection, and least squares and the use of randomization thereof, there are the talks of Eugene Nakatsukasa and Lisa Rebrova. When it comes to SDG, the two talks that follow mine by Courtney and Aliette Paquette, and later on by Dimitru Sviatsky. When it comes to sketching and random embeddings, which I've already mentioned, there will be a talk by Curtis. Zhou Fan was going to talk about PCA. Relationships between random matrices and neural networks and machine learning will be the focus of talks by Pennington and Mahoney. Jess Banks is going to talk about essentially smoothed analysis. Alan Edelman, Rachel Ward, and a bunch of other people are going to talk about random matrix theory tools that can be used in numerical linear algebra. And there will be a certain number of other talks that will deepen understanding and we'll talk about not just, I mean, special structured matrices. There will be talks, of course, the other mini course will be given by Sean O'Rourke, and he will talk about eigenvector localization properties thereof. So this is the picture of what the conference is going to be like, albeit it's a limited and not comprehensive one. Okay. So, all right. We've talked about the history, about what's to come, but there's the legitimate question of why are we even talking about this? Why do we want to randomize? What's the purpose of introducing randomness? How can that make things better? And the answer is, well, we're not dealing with things very well with classical methods. And part of that is the reason that, you know, when classical methods were considered, were introduced and were set up, the world, the computing world looked very different. And it certainly, I can't imagine that in the wildest dreams of say, von Neumann, he would have imagined the kind of data sets and matrix sizes that we're dealing with today. So the advent of data science and the fact that there's so much data out there that can be mined and used to make predictions, to make recommendations, to understand preferences and so on, makes it imperative that we develop better tools to deal with it because it's just too large. Oftentimes, we're talking about matrices that will not fit in the fast memory. And therefore, things like communication and so on, parallelization become extremely important. So there are all sorts of novel challenges that, during the last century, when the numerical linear algebra was being set up, were not necessarily at the forefront of research. So what are some of these challenges that I mentioned? Well, first of all, the complexity of the algorithms may be too large. We know, in theoretical computer science, people love to talk about polynomial time algorithms. But polynomial is as polynomial does. And an algorithm that's O of n cubed or O of n to the fourth is not really usable, especially for large matrices. And so we really have to talk about rearranging things or starting out with new principles that will allow these complexities to be brought down. Of course, complexity hides some things in it as well, which are the fact that sometimes algorithms that appear to work perfectly well and have lower complexities hide huge constants into them. So they may not be practical. But anyway, so this is something to take into account, the complexity of classical algorithms. Classical solutions to algorithms may not be designed to block, to use block matrices and operations with block matrices, and to use parallelism to the extent to which we understand it can be done today, and to the extent to which we have to implement if we want to make use of all of these wonderful new computer architectures. So that's another reason why this is a challenge. As I mentioned, matrices are so large that they may very well not fit in the fast memory, which means that they have to be stored on slow memory. And therefore, data has to be transported either from slow memory to fast memory or between different processors. And these transportation costs, as we will see in the second part of my mini course, come with their own problems, which is that every year becomes faster and cheaper to do an arithmetic flop than to transport a word across the memory hierarchy and so on. So these are very serious challenges. Like I said, there are these new wonderful computer architectures, starting out with GPUs, multi-core and distributed systems. But so in some sense, they're prime, they're ripe for the taking. They have been designed to facilitate things like parallelism, and they have been designed to be taken advantage of when it comes to things like communication issues. But that means that we need to reorganize linear algebra to make use of them, to really exploit them at their best. Maybe exploit is not. Well, when it comes to tools, I guess exploit is okay. So this is why we should randomize. Randomization may provide new solutions to these problems. It may provide ways to deal with these issues and even beyond. There are cons. So there are arguments against randomization, and they go in the way of criticizing Monte Carlo methods. Basically saying that Monte Carlo methods, or for Monte Carlo methods to work, what you need is concentration. And of course, if the variance of whatever quantity you're trying to compute turns out to be on the same order as the expectation, then a Monte Carlo method is not the variance, the standard deviation is on the same order as the expectation. Obviously, the Monte Carlo method is not going to bring you too much. If the fluctuation, if the outcome fluctuates that wildly, you can say that the expected value is closer to what you should truly expect. But in many cases, that's not true. So in many cases, we do have concentration results that tell us that the expectation of, or the expected value of a runtime or the error of an algorithm or so on actually do obey concentration principles and therefore can be used accordingly. course, there is a certain reluctance that I noticed in people when it comes to random outcomes. Somehow people are still not very comfortable with randomness. They like to have things deterministic. They like to see things reproducible. They don't like to see algorithms that produce different outcomes depending on the seed of the pseudo or random generator, for example. But this is more of a mental barrier that I don't think it's really there. So this is just something that we have to come to terms with. That a random outcome may very well be a typical outcome. What are the pros? Well, as it turns out, and as I hope I will convince you in the course of this mini lecture, mini course, I'm not sure what it is. It's not really a lecture, but I feel like I'm going to be talking almost continuously for 4 hours or close to 4 hours today. So this long discussion that I will have, or the long peroration, if you're so inclined, that I'm going to give you today. So some of the pros are that we actually can use randomization to ensure good outcomes. It's not always clear if a numerical linear algebra method will converge. They will converge, but in certain cases, and there are exceptions, and there are exceptions to exceptions, and so on. Most of the time, that's how it is. But sometimes, if you introduce a little bit of randomness, then you can say, okay, now I know that with probability, 0.999, it will converge in no more than this many iterations. So that's a very good outcome. We can introduce probability to achieve speedups, to reduce that complexity that I was talking about. And even usefully, in the sense that the constants involved are not going to be higher than the number of atoms in the universe. There will be at least one algorithm that I will talk about in this peroration that will have a constant that's like that. So there are, these are the caveats, but most of the time we don't. So these are speedups. Now, the thing about introducing randomness is that oftentimes you can take very simple ideas, very simple algorithms that are based mostly on things like matrix multiplication and the QR algorithm, which are both blockable and parallelizable and have lots of other beautiful properties, and use them extensively to do things with them. And if you do that, if your building blocks are good, and if you only use these kinds of building blocks, then the outcome will also have the same properties. It will turn out that you can introduce randomness in order to minimize the communication that I was talking about in, for example, eigenvalue problems. And this is going to be part of what I'll be talking about in a second in the afternoon. And in the case of smooth analysis, and this is this beautiful concept that was introduced in the early 2000s at MIT by Dan Spielman and Shan Kwateng. Both of them have now moved from Boston, but have been really the fathers of this subfield of that's at the intersection really of scientific computing and theoretical computer science, smooth analysis, which basically says if your algorithm works in practice much better than you expect it to, what that probably says is that the singularities in the problem are localized. And so if you introduce a little bit of perturbation in your input data, you're going to get off the singularity and it's going to be manageable. And this is the idea of smooth analysis. So Jess Banks is going to, oh, actually, I'm not sure that Jess Banks is going to talk about smooth analysis, but she's one of the folks who have been at the forefront, the cutting edge work in smooth analysis these days. So we'll see. Okay, so just to quickly convince you, although looking at who's in the audience, I think that most people are already convinced, but let's just take a quick look at how we can introduce this little bit of randomness into the power method to make it work the way we expect it to. So take a positive semi-definite matrix. Suppose that its largest eigenvalue is lambda 1 and lambda 2 is the second largest. We want to estimate lambda 1. Of course, this is what you do in the very first numerical linear algebra course that you take. You know that you start with some input vector. You normalize it. Here I'm normalizing it by dividing by the 2 norm, but I think that the first time that you see something like this, you generally normalize to have the highest entry equal to 1. That makes convergence better, but this is a perfectly good way to normalize. So you normalize it so that you put it on a compact and you can talk about convergence. And then what you do repeatedly is you hit this vector with the matrix and you renormalize, and you hit the vector with the matrix and you normalize, and so on and so forth until convergence. And convergence is defined in a couple of ways. You can look at the progress that you make from step I to step I plus 1, or you can just give it some certain tolerance that you want to achieve, or you can just take a certain number of iterations, which you know a priori that is going to be about enough. Now, this algorithm produces an estimate for lambda 1, and the error is given here. So the error is 1 minus the estimate over lambda 1. Of course, the error we don't have access to, but since we're going to analyze this theoretically, we can look at it as a theoretical object and see what happens to it. Now, this algorithm can fail in many ways. And actually, what I like to do when I teach numerical linear algebra is to pose all sorts of scenarios for my students that essentially leads to the failure of this algorithm, and to see exactly how it fails. It will fail because it doesn't converge, or it will fail because it converges to some other eigenvalue, and so on. So it can fail in many ways. Basically, you need to have a component in X1 in the direction of the eigenvector for lambda 1, and it helps if there is only one eigenvector for lambda 1, so if lambda 1 is simple, and so on. But you can prevent that, most of the time at least, by choosing a random input. So what I'm doing here is I'm writing x sub 0, so this is the original input, is chosen from the Gaussian distribution with mean 0 and variance I. So this means IID variables. So the covariance matrix is IN. That means that we have IID variables, which are all standard Gaussians. So if you pick your initial vector like that, then, and this is a result from 92, the expected error at step I is no larger than some constant log n over I. So this is a result of Kozinski and Wozniakowski, and it does not matter whether or not lambda 1 is equal to lambda 2. Basically, what this is saying is that after about logarithmically many steps with some large constant, the expected error is going to be small. It doesn't say anything about the probability of the error being small, but you can work that out. And then Joule-Trop kind of like refined this a little bit. I'm not sure if this result was new at the time that he wrote the proof, but I couldn't find other references to it. It's kind of, you can see it in here, but it's not explicitly written out. It is, however, written up in one of Joel's papers from 2018. Basically, what it says that if we know that there's a gap between the first and the second eigenvalue, then the expectation goes down again logarithmically. If you look at what happens here, it's logarithmically, but then it has much better control over how this goes. So basically, this is telling you that you don't need to worry about how you should choose your initial vector, that you should choose it randomly. Okay? And then your algorithm will work, provided that you take enough steps. Okay, so this is the simplest example, the one that can always be offered to kind of like set up the terrain and convince people that, yes, okay, randomization might actually have something to say. Okay, so in everything that I'll be saying next, I'm going to the singular value decomposition is going to play a very important role. And I'm going to go quickly over this. Oh, hi, Ken. Yes, so you can work out. So there are some concentration results that can be obtained, but I think it gets a little bit more. Yeah. Okay, so the singular value decomposition, which again I expect that everyone here knows about. Every matrix has a singular value decomposition, which is not unique, but basically it has U sigma V star, where U and V are orthogonal matrices of different dimensions that correspond to the two dimensions that the matrix has. And sigma is diagonal with diagonal entries in decreasing order, positive entries that are the singular values. The columns of U are the left singular vectors, the columns of V are the right singular vectors. And you probably all know that the meaning of this decomposition is that when you're mapping Rn into Rm or Cn into Cm via this matrix, then the singular values give you the way in which the unit sphere changes. The unit sphere in Cn becomes an ellipsoid in Cm, and these values, sigma 1 through sigma minimum of Mn, are the lengths of the semi-axis. And the left singular vectors and the right singular vectors tell you how this mapping is being done. So basically, if you know this, you know everything there is to know about the transformation and ergo about the matrix. Okay. Other ways of writing the SVD. This is the most important, perhaps, other way of writing the SVD, which is takes advantage of the fact that the UIs and the VIs are orthogonal to each subset. And you can write this matrix as a sum of essentially rank 1 matrices UI VI star, like this. And this helps you find low rank approximations. So if for some D that's less than or equal to the minimum of M and N, you define the truncated SVD as the same sum, but now instead of going up to the minimum of M and N, you go only up to D, then this matrix, this new matrix A sub D, solves the problem of finding the closest matrix of rank less than or equal to D in 2 norm for A. And amazingly, at the same time, this is also true if you replace the 2 norm with a Frobenius norm. So it's not often that you take different norms and the answer to the argmin problem is the same. This is one of these instances. So this Eckhart-Young-Mirsky theorem is very important, and we'll be using it shortly, actually. See, I have to hurry up a little bit. Okay. So this is for the singular value decomposition. Okay, and I thought that as one more motivational subject that will kind of lead into the next part of my talk, we should talk a little bit about Pca and dimensional reduction. Okay, so principal component analysis basically is a way to deal with a cloud of data points that you suspect have a smaller true dimension than the one that is observable. Maybe you have lots of points in a very high Euclidean space, and you want to find a way to encode them faster and better. Excuse me. So one way to do this is to assume that these points come from perturbed data. So there's some ground truth plus a little bit of Gaussian perturbation to that. And they're all lying around some d-dimensional affine space AD. And of course, and it's hard to imagine these things in multiple dimensions. So I've been lazy and I've just done a two-dimensional illustration. This affine space in this case is a line. It's affine because it's not a vector space. So it's a shifted vector space. It's not a line going through the origin. It has some other intercept. and these points are lying around it. Okay? And suppose that I want I have lots and lots and lots of points. In this case, I guess D is not much less than M, because it would probably be better if I could do this in like dimension 10 and have a single line, but let's pretend that that's the case. The question, of course, is how do we find this affine space that approximates the points? Because if we have that, then we can make predictions. So the way to do it, and I apologize for the statisticians in the audience because I'm not a statistician and it's possible that I'll say something wrong. The way to do it is to set up a maximum likelihood estimator and to find this affine space. And this affine space, as I mentioned, is a shifted vector space, which is d-dimensional. So basically, how can you find this? You can find it by an orthonormal basis for it. So you can find BD by an orthonormal basis for it. And you can find Z, you can find AZ that will work. An affine space is not defined by a single shift, it's defined by an infinite number of shifts. Essentially, anything that's a point or a shift plus a point in the vector space is going to give you another shift. That works. Okay. So basically, the setup is then this: you want to find the quantities that minimize this. So you want to project this vectors a sub I onto an affine space, which is given by Z and by an orthonormal basis for BD. Or essentially these squares. Heuristically, you can see that Z should be taken to be the mean, because if they're around that, then basically if you average it out, that's going to be a good shift. But this is heuristically, you can show this rigorously with calculus-based methods that it works. And then it turns out that Q is going to be represented by the first D left singular vectors of the centered matrix A minus Z times the transpose of R. So this is you take away Z from every single one of the AIs, you get this matrix A bar and you do its SVD, and Q is going to be the first columns of. And I'm going to just sketch the proof and leave it here. So basically, I've already argued why the shift Z should be what it is. You can make that rigorous. Then, if you know Q, then this is a least square problem. So if you know AI bar and you know Q, solving this problem, finding the beta sub I, which is best, which minimizes this is given by Q star AI bar. So this is something that we
once you are regular,
and now we have boiled down the problem to finding Q, because the problem is expressible now like this. So we know what Z is. We know that AI bar is the quantity we should be looking for. We know that the beta i's are going to be Q star AI bar. So the question is to find Q. But it turns out that this has a very simple expression as a Frobenius norm. So this sum over here is just the Frobenius norm of the matrix A bar minus Q star A bar. And by the Eckhart-Yang-Mirsky theorem, the minimum is achieved if and when you make Q star A bar is equal to A bar T. Okay. So if we can find a Q that does this, then that's the best you could possibly ever obtain. So that has to be the solution. It turns out that, yep, you can solve this. And it is given by the first D columns of Q. Okay? So we will see a lot of this in the coming couple hours, 2.5 hours. I'm not sure exactly how much time I have, but essentially this is solving problems of this kind, finding ways to approximate Q without actually computing it outright. So this is what low rank approximation is going to be about. Okay, so the conclusion for part one is that random choices can lead to good outcomes. The SVD and the truncated SVD, so that A sub D is the answer, is a true answer to low rank approximation, assuming that you have exact arithmetic and a whole lot of other idealized properties. The one downside to using the SVD is that it is not easy to compute. So we know that the SVD can only be obtained by iterative methods, and this is a consequence of the Abel-Ruffini theorem, and therefore it takes a certain amount per principal component to get it. Things are not always guaranteed, and so on and so forth. So this is the only issue that remains. And I think, okay, and this is it. I'm going to stop now. I'll take a few questions, and then I guess we'll have a 5-minute break. Continue my peroration. Okay, so with this introduction in mind, let's go on and talk about some of these numerical linear algebra algorithms. What kinds of algorithms you have, what kind of randomization you can insert, what kind of guarantees you can get from the randomization. Oops, I'm sorry, Tom, this doesn't seem to. Oh, okay, thank you so much. Okay, so before I delve into randomized low rank approximation, let me talk to you about the deterministic low rank approximation. So we have seen that the truncated SVD provides the best low rank approximation for a matrix. Of course, this is kind of a difficult thing sometimes to compute. It takes a long time to get it. There are caveats and so on and so forth. So we're going to try and find alternate ways to do that. Okay, so as I mentioned before, computing the SVD is tantamount to computing eigenvalues. Abel-Ruffini tells us that there are no direct methods to do it. Therefore, all we can do is iterative methods, more or less involving simultaneous applications of the power method. And therefore, each one of them takes about O of m n arithmetic per singular value or n eigenvalue. There are several ways to speed this up, but not significantly in the sense that you can reduce the constant, but you can't really, classically speaking, you cannot bring that mn part down. And in certain cases, the complexity can actually well surpass. So the worst case scenario can be pretty bad. So this is not to ignore. But there's also another question that I'm going to try and answer this afternoon is, okay, so suppose that what I'm trying to do is build an eigenvalue algorithm or a singular value algorithm that takes advantage of some of the things that I mentioned before, that's parallelizable, that's blockable, that can be used to minimize communication and so on and so forth. If I want to do that, I probably shouldn't count on using SVD or Eig inside of it. So if you want to build it from scratch, you're not going to be able to use the truncated SVD as a low rank approximation. Therefore, you have to find other methods. Okay, so how do we do that? Well, this is a setup, a kind of a proto algorithm. And I'm using the nomenclature from Martinson and Tropp's 2011 Halko Martinson and Tropp's paper, Proto Algorithm, which basically says the following thing. First, you have to find a matrix Q that makes, well, it doesn't necessarily minimize this quantity, let's say the 2 norm or the Frobenius norm, mostly the 2 norm. We're going to talk about the 2 norm in this series of lectures, but you can also do this sometimes with the Frobenius norm, although not for every single algorithm that I'll mention. You want to find a matrix with orthonormal columns, which somehow makes this quantity small. And the point excuse me, the reason why this is called a range finder is that the range of Q approximates the range of A. So because Q represents an approximation to the first D left singular vectors of A, it approximates the range. That's more or less what it does. That's why this is called the range finder. So the first thing you do is you find such a Q that makes this norm small, and then you restrict A to the space defined by the columns of Q, and you find an approximate SVD for the matrix Q star of A. And then you output, you make your Q better by taking it, multiplying it with the left singular vectors that result from the SVD of this matrix Q star A, and you make it better. Okay. So these are the two stages that I'll be referring to a lot. The first stage again is finding the Q and then restricting A to the column space of Q and finding an approximate SVD there. And that's going to be your you can also use sigma and V star at that point. So if you want to find a low rank approximation or an approximate SVD, then you would do both stages. If you just want to find a low rank approximation, then QQ star A is going to be sufficient. So the range finder is enough. Okay, you can do this deterministically. You can do it entirely with the SVD. And as I mentioned before, the complexity is going to be big O of M and D. In practice, it can get much worse than that, depending on the properties of the matrix. But you can do other things too. You can find a so-called rank revealing factorization that looks like this. A pi is equal to QR, where pi is a permutation matrix. Well, it was defined as a permutation matrix, but really it can be thought to be some sort of simple enough structured matrix. Q is orthonormal, sorry, it's orthogonal. My bad, I should not have written orthonormal. I just taught math 18 at UCSD, so linear algebra, and I had to explain to students all the time that even though the matrix has orthonormal columns, we don't call it orthonormal, we call it orthogonal, and here I am making the same mistake. Sorry about that. And R is block triangular. So this is what's called a rank revealing factorization. The first types of rank revealing factorizations were introduced in 1965 by Bussinger and Golub, and they work well in practice, but again, they have worst case scenarios that are not so great. There have been many other attempts which have either produced, I mean, these two that I mentioned here actually produced pretty good rank revealing factorizations, but it can take a really long time to obtain them. Again, worst case scenario. But the best deterministic rank revealing factorization at the time and still today was introduced by Mingu and Stanley Eisenstadt in 1996. And they also defined this concept of a strong rank revealing factorization, which I'll explain in a moment. So basically what they did was to show that the composition of the following form exists, and then gave a very good way to get it efficiently. So the composition is of this kind. Oh, I forgot the Q. There's a Q in here, apologies. So A pi is equal to Q times this block triangular matrix, which stands in for R, that has the following properties. So all the singular values of the first block are well approximated, or are good approximations, not too big or not too small approximations to the singular values of the matrix A. Now, what do I mean by that? In particular, what matters is that sigma sub D. So if the numerical rank of the matrix A is D, sigma sub D of AD is not much smaller than sigma sub D of A. Now, not much smaller, this has to be taken with a grain of salt because Q1 of Dn, which is this ratio, is actually going to be a polynomial in Dn. And it's not going to be, so the best polynomials are roughly like square root of D square root of N. Similarly, for C sub J, the singular value, so for C sub D, the singular values can also be well approximated. They don't grow much faster than the rest of the singular values of A. Okay, so this is the same Q1 as before. So what this is saying is that for this to make sense, really, you've got to have that sigma sub d of AD and sigma sub d plus 1 of CD are separated. So you'd like to see that the sigma sub d of AD is still much larger than sigma sub 1 of C sub D. That would be a good strong rank revealing factorization. And that can be done if you have a big gap to begin with. Okay, because this rank revealing factorization is going to cut into that gap. Okay, so you need, for this to really work well, you need to have a big gap at the level of sigma sub d of A to sigma sub d plus 1 of A. And also you want to have that this B sub D is not too large. Okay, so this is not taking you too far off the ranges. Okay. So this is what a strong factorization is. So for Q1 and Q2, small degree polynomials in D and in D. This is what the definition of a strong rank revealing factorization is. And what Mingu and Stanley Eisenstadt showed was that if you pick some f larger than or equal to 1, you can pick Q1 and Q2 to be respectively f root the n and f. Okay, so yes. Oh, basically it says that the spaces are also going to be fairly close. You know, because in principle you could get very far away. But this is what this is saying. So it's saying that truly you will get a decomposition in terms of this matrix Q that tells you where the left and right, I wouldn't say eigenspaces, but left and right spaces are for this matrix. Okay, so this works in roughly O of M and D flops again, so which is about the same as for the SVD, but it's the important thing is that it's stable. And if you take F to be like a tiny power of n, then this is about the right complexity. So this is the best to date deterministic rank revealing factorization. It's a complex. Oh, sorry, it's a complicated algorithm. It's not easily blockable and it's not easily parallelizable. In fact, I'm not sure that there have been really strong efforts to do either. Stage B for any of these range finders that I'm going to be talking about is going to be deterministic. You'll find the SVD of a small matrix. It's relatively cheap. Again, we're operating on the principle that D is small compared to MNN or to the minimum of MNN. Okay, so the biggest cost for such an algorithm for low rank approximation, stage A and stage B, comes from this OMND from stage A. And as I mentioned, it's a little unwieldy. So these algorithms are a little unwieldy and they have not been shown to do cool stuff like minimizing communication or any of the other kinds of things. Okay, so most of what I've told you, well, not most, a good part of what I've told you before is also present in these surveys. Oops, and I misspelled Joel's name. Sorry about that, Joel. In these surveys by Halko, Martinson, and Trop, and Martinson and Trop. And these descriptions of the algorithms that I will mention here in the second part of my peroration are going to be hewing close to that as well. Now, the idea is, how do we insert randomness? What's the problem here? What's the real problem in finding the range? Well, the problem is that we don't know. I mean, the columns of the matrix are distributed arbitrarily, which means that you could have columns that are not strongly contributing in any way, shape, or form fairly at the forefront of the matrix. Okay, and you might have to go very far in the back to find the ones that you want, but you're not going to know that. So instead, if you scramble the columns, if you hit them with some orthogonal matrix and scramble them, or some random matrix, and scramble them a little bit, then perhaps you're going to draw those significant vectors more to the front, and you're going to be able to get away with doing less computation. So this is the idea underlying the algorithms that I'll be talking about. You pick a small random matrix. When I say small, basically what I mean is that it's going to have few columns. It's not going to have exactly as many columns as you want, for reasons that will become apparent later. You'll have to take a few more, at least. But it's going to be relatively small compared to the other two dimensions. And it's relatively easy to produce such a matrix. And if it's truly random, then what you're going to end up with is you're going to extract the important information from the columns, and you're going to be able to operate based on that. And then you will do QR on this new matrix A omega. This is much smaller. It has D prime columns. QR is going to be much less costly, and then follow with stage B. Why is this interesting, important, desirable? Because it's very simple. It's very, very simple. So all you have to do is generate a random matrix. Then you do matrix multiplication and QR. Both matrix multiplication and QR are very nice algorithms. They're parallelizable, they're blockable, they avoid communication, they do all sorts of things. The simpler the blocks that you build your algorithms from, the easier it'll be to show that it does things that you want it to do. So that's why this is desirable. Okay, the runtime of this Proto algorithm, I didn't tell you how to generate the random matrix, mind you. So there are many ways to do it, we'll see. But the runtime is here. And you can actually do better than that. You can pick an omega, which makes the multiplication, which is the costliest thing. Constructing this y is the costliest thing. That's what gives you here the OMND prime factor. But if you choose omega wisely, you can make this multiplication faster and reduce things not to mn d prime, but to mn log d prime. Okay? And the way to do that would be to construct an omega which makes multiplication faster. And if you've taken numerical methods, you might immediately think about the fast Fourier transform. And that is indeed how we will construct the omega here. Okay? That's what will allow us to reduce this d prime from d prime to log d prime. Okay, so these are the algorithms that I'm going to talk about. The extra costs are to generate omega, but this can be done relatively on the cheap. And the extra costs also come from the fact that you're going to produce a lower rank approximation that will, at least on the face of it, have a larger rank than you'd like. But in practice, not much larger. So as we will see, this difference is what will give us probabilistic bounds. So the larger this difference, obviously, I'm going to say something that's probably very clear. The larger d prime is, the better the probabilistic bounds we're going to get. But in practice, it'll be sufficient to take it just, 5 to 10 higher than d. Okay. So it's not, we're not going to have to go very far. So that's yes. Oh, sorry. So that's the idea. So the simplest way to do it is to choose a Gaussian matrix. So a matrix of IID Gaussian variables. And for this one, this Proto algorithm yields an expected bound, which can then be transformed into a probabilistic bound, which just looked like, it didn't look, if you think that this doesn't look nice, you didn't want to see that one. but it can be done using very basic probability techniques. And it gives us an expected value of this error to be on the order of square root of d sigma d plus 1 plus square root of d prime times the Frobenius norm, so to speak, or the 2 norm, if you want, of the rest of the singular values. Okay, so there's these 2 parts tell you something about the dependence on sigma d plus 1, which we expect. But it also talks about the fact in which things are going to be affected by the fact that the singular values may decay fast or may decay very slowly. Okay, so there's this this controlling bit, which will tell us what the difference is. Okay, at worst, this will give us this c square root of d minimum of m and sigma d plus 1. And I will remark about the fact that this is very similar to what I just said about the deterministic strong rank revealing factorization. It's on the same order. So the error is on the same order. Probabilistic and cheaper. Do you have a question, Shihan? Yeah, go ahead. They're small constants. I think that I'm bearing here, this should be a square root of d over d prime minus d minus 1 or something like that. Maybe it has an epsilon on it. So not an epsilon, sorry, an e. So they're very small constants. The constants are independent of a, yes. So the dependence on a is given solely through these sigmas, yes. They may depend on, they can be taken to be absolute constants that do not depend on a. Yeah. Okay. I mentioned the fact that you can transform this bound into a probabilistic one. And notably, the failure probability is proportional to this difference between d prime and d taken to minus itself. So basically, you see why 10 is sufficient. 10 to the minus 10 is very small. So basically, this is where we want to do to take a little bit extra, but it doesn't have to be too much. So this is what happens for Gaussian entries. Again, this is I just copied the bound over from the previous slide. The important thing here is that it works always for any d, n, and m. We will see that if we give something up, then it might not work all the time. When there is a significant singular value gap, so that sigma d plus 1 over sigma d is very small and the singular values decay very fast, and basically this term is not going to matter so much. And the bound is going to be comparable to sigma d plus 1. Well, it'll have this extra square root of d. But we know that in reality, the best that you could ever get is sigma d plus 1. And so it's going to be relatively comparable. But if that's not the case, then the bound is still comparable to the best deterministic rank revealing factorizations, because what you get here is another square root of n, essentially, or square root of n minus d. So this algorithm, you know, if you have quick decay, then it's comparable to the SVD. And if you have slow decay of singular values, then it's comparable to what the best rank revealing factorizations would give you. It also works when you don't take any extra quantities, but the probabilities are much worse, and you get an extra factor of square root of d. So instead of having this be a simple square root of d, you're going to get a d. So that's, and the rest of it is going to also be multiplied by a square root. I don't know what that was. Okay. Okay, so, but that's one thing that we can do. An alternative, which I mentioned already, is to pick a matrix that we know will allow us to multiply things faster. And this will be a subsampled random Fourier transform if you're working over C, or something akin to it if you work over R. I'll mention it in a moment, cosine transform or a Hartley transform. Basically, what you do is the following thing. You have this Fourier matrix, Fourier transform matrix, and you take a few random columns from it That's the effects of R. So R is just taking a few random columns of the unity. If you multiply by R to the right, you just extract a few random columns from F. And then you take this D matrix, which is just a diagonal matrix of phases, you just rotate things a little bit. So note that there's very little randomness here. There's very little randomness. Before, we would take a full matrix of Gaussian. So that means Mn, or sorry, M D prime Gaussians. But here, you only have D plus N variables. So much less randomness than in the previous case. And it turns out that, so I mentioned that you can use other things if you're working over Rn or cosine or a Hartley transform. I think that the Hartley transform is probably better. The extra benefit is that when you compute A omega, then you use the fast Fourier transform and you can reduce the complexity of stage A and the matrix multiplication of stage B for an overall Mn log D plus N D squared complexity. So better than before. Of course, what you need is a very good FFT implementation. In the absence of that, you're not going to be able to do this. But given that, then this is how you can go about it. Okay, the guarantees are a little weaker. In particular, as I mentioned before, for the Gaussian, you could do this for D, M, and N being whatever you wanted. Here, at least on the face of it, you have to take D prime much larger than D. In fact, it has to be on the order of log N plus D log D. So whichever one of them is larger, D or log N, you're going to have that times log D. This, of course, restricts D. Now you can't do things like take assume that your rank is proportional to the size. You can't do that anymore. But you can't do that in theory. It turns out that in practice, you know, in the absence of this theoretical guarantee, if you just let D grow to being proportional to N, you can still get very good results. But there are no theoretical guarantees in that range. Why is this extra log factor necessary? Well, it turns out to be more of a coupon collector problem. So what you're trying to do is sample the important columns to really, there's D of them, to make sure you get them, you're going to have to do about D log D samples or N log D samples, depending on which one of them is bigger. So you can't get rid of it, okay? Because it's, you know, it's a coupon collector problem. And the bounds are a little worse than they were before. So now you get that the difference here now, instead of being on the order of square root of D, is going to be square root of N over D. But that's still pretty good. However, excuse me, what's not so great is that the probability of failure is now much larger than before. So before, remember that the probability of failure was controlled by how many extra columns you were willing to take. And if you took 10, you know, that was very good. But now the probability of failure is D to the minus 1. Okay. In some sense, this is a consequence of the fact that there's much less randomness and much less concentration as well. So, you know, you can get speed ups, you can get this factor of D in the complexity reduced to log D, but it comes at a cost. As always, things in life are always involving trade-offs. Okay, so these are real theoretical obstacles, but in practice, as I mentioned, that the method of using this subsampled Fourier transform, it works as well as if you were taking a matrix of Gaussians, especially if there's a gap. Okay. Now, these are two main ways of constructing these approximate range finders, but both of them can come with enhancements. So there's other stuff that you can do on top of it to help it out. For example, if the singular values decay slowly, you can speed that up by coupling things with the power method, essentially. So you can inflate the gap by using the power method. So essentially, how do you do that? You pick some exponent q and form y to be a star to the q omega instead of just a omega. This is enough because the ranges don't change. And so you're trying to approximate the range. So that's fine. But now the singular values are going to be much further apart. And in practice, to make this even better, you could do repeated reorthogonalization. So you raise it to one more power, then you orthogonalize y to be just its QR factor, then you raise that, then you multiply that again with a star, then you orthogonalize it and so on and so forth. So there are ways to do this to make it better, to ensure stability. Of course, this comes at increased arithmetic cost. And again, what you do is you drive the singular values apart. And based on this lemma here, which was shown by Halko, Martinson, and Trop, you can reduce this bound by a factor of 1 over 2q plus 1. Similarly here. So this is a translation for that in some sense. It's a slightly worse bound. So you can do better than you would normally do. And it turns out that you don't have to go very far with q. So in practice, q is 2 or 3 is sufficient. If the singular values are almost flat, then you could go as far as logarithmic. But in practice, that's not the case. Okay, now the complexity now becomes O of q, m, and d, which is why you want to keep q small so that it's not actually a parameter in here. But this is enough, sadly, to kill off the SRFT advantage. So this will work for the Gaussian. If you're working with the SRFT because you want to do matrix multiplication faster, this is not going to help you there because it's just going to change the complexity back to what you were trying to get away from. Or alternately, if you know the power method is not enough for you, then you can use Krylov subspace methods. So instead of working only with the last power, you can work with a whole bunch of powers of the matrix. You construct this very large sample matrix and use QR to find an orthonormal basis. Normally, the way that Bloch-Lanczos methods are used are very effective when the sample size is small and Q is large. In this case, we're trying to use it the other way around. We would like to make D prime relatively large and Q small, but experimentally, it can be shown that it still works. Because the reason why we want to do this is that this regime is best for computer architecture, where you basically want to block and to use the size of the blocks to be as big as possible, which is why you want D prime large, not Q. And as long as the gap is of medium size, not too small, then it still has pretty good performance in practice. Okay, so these are, and the guarantee now looks something like this, and it's slightly better than what the power method would give when epsilon is small. Okay, so you can do these enhancements. Of course, when you do Krylov space methods, then what you need is more storage, and of course, the arithmetic cost is going to be higher. There's also the downside that without further enhancements to the Krylov rangefinder, you might run into instabilities. And so you probably want to do more stuff to stabilize that, which will in turn raise the cost of storage and arithmetic. Okay, but I think, am I about, okay, so this is better than last time. Basically, I'm going to conclude the second part of my lecture by saying that the reason why these randomized rangefinders are desirable and they're actually quite used in practice these days is because they're simple. They're very simple. They are blockable, they're parallelizable, they minimize communication, they allow for, in many cases, they allow for a single one pass through the data, which is very important in reducing communication, and you can prove that they will work with high probability. And there are again trade-offs. So you lose some of the accuracy if you want to do it faster and with fewer random bits. But the surprising thing is that you don't need very much randomness to do it right and to get some sort of guarantee. Things to keep in mind is that we're generally talking about cases when the rank is much smaller than n. And these things work, of course, well when there's a gap between the singular values, which is, the assumption that the numerical, what you're trying to do is estimate the numerical rank of the matrix, as opposed to just arbitrarily cut it off somewhere and say, okay, this is going to be good enough for me. And these methods also work acceptably when there isn't much of a gap. And in addition to the basic rangefinder algorithms, you can add these simple enhancements that will preserve the properties that you want, but increase the cost of storage and arithmetic. And this is the last thing I'm going to leave you with, because it's going to be the first thing of what I'll do when I come back. Most of the bounds and guarantees that I've talked about here are based on expectations and good estimations of the 2 norm of the pseudo-inverse of a random matrix. So the 2 norm of the pseudo-inverse of a random matrix is the smallest singular value, so it's 1 over the smallest singular value of said random matrix. So if you have good control over the smallest singular value of said random matrix, then you get good control over this pseudo-inverse 2 norm, and therefore you can give good bounds. So that's the thing that we'll be talking about next: smallest singular values of random matrices. Okay, thank you very much. You hear me? Can you hear me? Yes, you can hear me? Okay, good.
Okay, so welcome back. And now we have Ioana round 2, back to randomize to optimize.
Thank you, Tom. All right, so I guess I'm going to round off the day until the poster session. I realized that I defined myself as being from the Department of Mathematics, but I didn't specify which Department of Mathematics, which is funny because many of you know that I've been in this Department of Mathematics until 3 years ago, but now I'm at UCSD. So if you look right here at the bottom, it actually says where I'm from, but you have to really squint. So yeah, so I'm at UCSD these days. Okay, so I'm going to start by recapping. Well, first of all, let me remind you a little bit before even we go into the set of topics that I'll be presenting in this last 2 chunks of my multi-part lecture. So we talked in the first half about randomized algorithms for things like rangefinder and low rank approximation, and the role that the SVD is playing and is not playing in constructing these algorithms. How we're trying essentially to mimic the SVD or the SVD for a larger matrix by either making computations for a much smaller one, or by avoiding that altogether and just doing some sort of other types of rank revealing factorizations. And at the end of the second part of my multi-part lecture or peroration this morning, which feels like an hour ago, which probably because it was an hour ago, I mentioned the fact that in all of the guarantees that we can give for these low rank approximations, the smallest singular values of random matrices seem to play an important role. So I'm going to start this part, the third part, with that. That's the plan. And then I will continue explaining a little bit more in detail the things that I've been alluding to in the morning about computing issues, what the computing issues that we're trying to deal with are, about the trade-offs that we can make in terms of arithmetic versus communication, accuracy versus speed, and so on. Then I'll talk about computing eigenvalues, so some particular algorithms for computing eigenvalues. And then I will refer to some very new work that's connected to that I've been doing with Jim Demmel and with Ryan Schneider, who's going to continue that on his poster outside right after I finish, or not right after, right? Because there's a break before that too. But anyway, soon after I finish this, and the connection with smoothed analysis and the work that's been done by a group of Berkeley researchers, one of whom, Jess Banks, is here. So you're going to get a chance to talk to her about her work and ask lots of questions as well. Okay, so that's the plan for the afternoon. So again, this is, recapping a little bit. We've examined what kind of relationships exist between low rank approximations and rank revealing factorizations, both deterministic and random. And I mentioned at some point that what we need in doing these estimations is proving these guarantees for rank revealing factorizations are good estimates for the 2 norm of the pseudo inverse of a tall, skinny, let's say, random matrix X. So in other words, we need to figure out what we can say about the smallest singular value of X, and in particular, how small it can get. So that's the plan. And there will be several kinds of matrices that we will be doing this for. Different kinds of random matrices. The first kind being the nicest and the simplest kind that we've been looking at today, and that is the Gaussian matrix. So, of course, the distribution of the smallest singular value of a Gaussian matrix, especially a tall one, so one where the aspect ratio of rows to columns is bigger than 1. These have been known for decades, going back to the work of Edelman, but also later on in terms of more refined results by Bai and Silverstein, all sorts of non-asymptotic results that were given later by Rudolphson, well, at the same time, I guess, by Rudolphson and Vershinin. Very recent, I've been exposed to this work by a postdoctoral researcher, Fan Yang, who worked with Jun Yin, actually, who is going to talk at this conference as well, who did some very interesting work on deformations, looking at the smallest singular value of slight deformations of Gaussian matrices. So basically, there's a lot that's known. And it's well understood. The trick is to keep the aspect ratio constant, and then you can talk about these distributions, the order of magnitude, and so on. But another important kind of random matrix that I want to talk about that turns out to play an important role in this business of low rank approximation and the rank revealing factorizations is the smallest singular value of a corner of a Haar matrix. And I'll define these terms in a moment. This one has gained prominence, and prominence maybe is too much said, but has gained some interest a bit more recently in connection with, like I said, this work. So let me define these concepts that I've been mentioning. So a Haar matrix is a matrix that is uniformly distributed over either orthogonal or unitary matrices. There's a Haar real distribution, and there's a Haar complex distribution. So you can think of it as the most natural kind of distribution that you can impose on orthogonal or unitary matrices. And one way to think of a Haar matrix is as the Q factor in the QR decomposition of a Gaussian and Bayesian matrix. Okay. Of course, if you plug it into MATLAB, you're not going to get quite that, because MATLAB, when it asks you for the QR factorization. It gives you a particular QR factorization. I think that the first entries have to be positive or something. There's some restriction, so you're not going to get the full gamut. But technically speaking, that's what should be. Okay, so that's what a Haar matrix is. A corner of such a matrix is essentially a subspace, is a submatrix with rows and columns extracted from the same set. So you choose a subset of 1 through n of size at most n over 2, and you take the rows and columns corresponding to that subset. Of course, because the matrix is IID, it means that you can think of it as exactly what I said, which is the corner, the upper left corner of the matrix. Okay, so that's what a corner of a Haar matrix is. And the question that is relevant to what we're doing is when R, so when the size of this matrix is proportional to n, can we tell what the distribution of the smallest singular value of that corner is going to be like? Can we tell that? This is not a trivial question, especially since these matrices are not immediately, seen as something very familiar. They are corners of orthogonal matrices. So their rows and columns will have norms that are less than or equal to 1, less than 1, almost certainly. And the entries are not IID because, again, the columns and the rows are orthogonal to each other. So these are, immediately seen what this could be. And yet, as we will see in certain cases, they are very close to models that we've seen before. So this is the question that I'm going to talk about. Now, these Haar corner matrices turn out to have eigenvalues, or sorry, not eigenvalues, singular values that are connected to the beta Jacobi matrix distributions. Now, some of the folks here know what I'm talking about when I say beta Jacobi, but I bet you that most of you do not. Some of you might get a clue if I talk about matrices connected with multivariate analysis of variance or MANOVA. But in either case, that's perhaps a little bit less relevant because that's kind of it's a well-known distribution random matrix theory, but you can think of it as slightly niche. And so I'm not going to say too much about that. I'm just going to talk about the fact that there existed this connection, and it was explored by Benoit Collins in his PhD thesis, which he published in 2003. Yes, yes, yes. It depends on R and N. Yes, both of them. Yeah. So the distribution is essentially the same. So the squares of the singular values, the eigenvalues of the Haar times Haar transpose are the same as beta Jacobi ensembles. No, I don't think so. Yeah, I'm not sure. Yeah, I would have to go back and check, but I don't think it's obvious. Yeah, so this is something that he wrote in his thesis and published, and so I'm thinking that it's probably not obvious. Okay, so these corner matrices have been studied very extensively by Chefeng Jiang from University of Minnesota. He's a statistician. Especially in the case when R and N go to infinity. But when R is much, much smaller than N, as they both go to infinity, in particular when R is like little o of N over log N. So he found out something extremely interesting, which is that basically there is a very simple relationship between these matrices and Wishart matrices. So it turns out that the entries of these matrices look almost Gaussian, normalized, like normalized Gaussians. So they can be approximated very, very well by Gaussians in this small R regime. And then from this, you can deduce all sorts of things, including all sorts of things about their spectra, exactly what you would expect from Wishart spectra. Now, of course, this perhaps is not so surprising because beta Jacobi ensembles, when R over N goes to 0, become beta Laguerre ensembles. So, but beta Laguerre is the same as, or a generalization of Wishart. So, so all of this stuff kind of, makes sense once you see the picture. You might not see exactly all of the details, but it kind of fits. So again, this is the regime when they were really, really well understood, but it's not the regime that we're interested in. So it turned out that when R is proportional to N, in certain cases, happily, ones that cover very nicely the cases that we are truly interested in, which are corners of R matrices, these beta Jacobi distributions can be computed. So they can be computed exactly. They can be then asymptotically, distributions can be asymptotically calculated in terms of, in the case of the beta Jacobi ensembles, by multivariate hypergeometric functions, which are kind of a complicated but beautiful object connected to all sorts of parts of combinatorics, and at the same time, Laplace-Beltrami operators and the like. But in the cases that we're interested in, which are the cases of real and complex corners of R matrices, they're computable in terms of univariate hypergeometric functions, which are objects that I think way more people are more comfortable with than the multivariate kinds. So there was some work that I did in 2012 because I needed to know what these distributions were like. And it turned out that you could do a little bit more. Okay, so like I said, these beta Jacobi ensembles are kind of niche, but this specific result turned out to be interesting, not just for me in the work that I was doing, but also for these rank revealing factorizations and maybe other things as well. Okay, essentially, what it allows for is a really close estimate of tails. So what this is saying is something like this. So the probability then 1 over sigma mean of one of these matrix corners when R, actually for this doesn't matter where R and N live. This is general for any R and any N, maybe bigger than or equal to 30. You can get that this is the probability that this is less than square root of R times N minus R over delta is at least as large as 1 minus 2 delta. So if you turn this on its head, what it says is that the probability that this sigma mean is greater than delta over square root of R times N minus R is 1 minus 2 delta. So they cannot get very small. Okay. In particular, the probability that this is small is, once you scale it by this factor of square root of R times N minus R, is proportional to delta, at most proportional to delta. So this is not, I don't think that this is extremely tight, but it was good enough for the purposes that I needed. And then Banks et al. So Jess Banks, Jose Garcia Vargas, I hope I forget his first name, Kulkarni, and Nikhil Srivastava looked at, as part of a larger thing, looked at the same thing for unitary R and got something similar, except that in this case, the probability is even better. It's proportional, failure probability is proportional to delta square, not to delta. Okay, so again, this says that if you scale them properly, they're not going to get too small. And this is important. It turns out that this allows us to evaluate the quality of randomized rank revealing factorization, which I will for now refer to shortly as RURV. Okay, so I'll ask you to put that on a shelf for a moment and go back to issues of trade-offs and complexity. So, okay, what do we mean by complexity? Any algorithm has its own complexity in terms of arithmetic. How many floating point operations or so many operations in total will there be executed given some size of an input? Essentially, that's what this is. But then every problem has its own complexity, which can be thought of as complexity of the fastest algorithm for solving it. And this complexity is not always known. And of course, the case in point here is matrix multiplication, which you will think of, okay, so this is a very simple problem, matrix multiplication, take 2 n by n matrices, how hard can it be to multiply them? Sometimes when we talk about the number of operations needed, we might think like a numerical analyst, which I guess technically I'm not, but I kind of pretend to be sometimes. There's a difference between counting addition and counting multiplication. Multiplication is somewhat more expensive. And so it's absolutely, or rather it's a common understanding that you can refer to the complexity of a problem by the number of scalar multiplications that you have to do. Okay? And so here's a very simple question. How many multiplications are needed to calculate the product of 2 scalar multiplications of 2 matrices, n by n matrices? And of course, the classical straightforward multiplication algorithm will give you O of n cubed. Because for each of the n squared entries of the matrix, you're going to have to do n multiplications. So overall, O of n cubed. Well, it turns out that that's not best. Of course, in the classical sense, this algorithm is very stable. It's entry-wise stable, which means that you can compute every entry, with a lot of accuracy and stably. But if you give up a little bit of that accuracy and think of stability as being norm-wise instead of entry-wise, then in 1969, Strassen showed that you can get away with much fewer multiplications. In particular, something like big O of n to the log base 2 of 7, and that's much smaller than 3. Well, okay, that's smaller than 3. This one is small. So the Strassen algorithm, which is also norm-wise stable, is actually starts getting the better of the classical matrix multiplication algorithm at small numbers, 50, 100. So this one is actually pretty small, and I think Anne knows what I'm talking about. Yes. So this one is an okay algorithm to use. Okay. So now we're going to say, okay, you can do this, you can do it well, it's better. Is it best? But maybe before I go into is it best, let me tell you why it's possible to do this. So it's possible to do this for a very simple reason. For a little bit more in terms of additions and subtractions, you can get away with just doing 7 multiplications instead of 8 when you multiply 2 by 2 matrices. Okay? So you trade a little bit of addition, a small number of additions, extra additions for 1 less multiplication. Turns out to be a good trade. So you scale that. You do block matrix multiplication, you recur, and you can extend it to yield this big O of n to the log base 2 of 7. That's Strassen's algorithm in a nutshell. And because it's simple enough, you don't get a very large constant here. I don't know what the constant is, but it's not large at all. Okay. Yes. So when you do block matrix multiplication, you don't have control entry by entry all that well. So you introduce several types of errors. So basically, it scales to the point where you get something like, you get better than norm. I think that it's actually norm, column norm. So Strassens is column norm, not just norm-wise accurate. When I say norm-wise, I mean the difference between the true value and the computed value is less than or equal to some polynomial in n times epsilon machine times norm of A, norm of B. But Strassen is even better than that. Yeah, but it's not as good as the classical one. Okay, so the best algorithm to date is due to Coppersmith-Vinograd from the 90s. They initially showed it to be big O of n to the 2.376. Now this is going to be funny. And then subsequently, it was polished in its analysis by Stodders, Vasilevska-Williams, Le Gall, and Altman and Vasilevska-Williams to O of n to the 2.3728. So a ton of work for a reduction of basically 0.0031 something in the exponent. Okay, mind you, it's the same algorithm, so they didn't actually do much with the algorithm, but they polished the analysis. Okay, so this shows that you can do better. The complexity is better. In fact, it is widely believed that the complexity should be not log base 2. When I'm talking about the exponent, it shouldn't be 3, it shouldn't be log base 2 of 7, it shouldn't be, certainly shouldn't be 2.3728, because that seems very arbitrary. It is believed to be 2 plus epsilon, if you want 2 plus little of 1 or just 2. And this is known to be obviously a lower bound, because you do have to make, you have to compute n squared entries, so you can do better than that. Okay, so that's where we are right now with matrix multiplication. It's an open problem. Solving it would bring you much fame, I think. I guess because there's nothing that's preventing it, that is obviously preventing it from just being 2 plus epsilon. I'm not sure. This seems to be a consensus. It's not of the kind, P is equal to NP, but it seems that it is believed, it truly is believed to be 2 plus epsilon. Okay, but the thing is, this discussion of complexity could be only academic, because the algorithms that can achieve it might be unstable, or certainly Coppersmith-Vinograd is unstable, or they could have overwhelming constants, so known galactic algorithms, meaning that they start achieving their asymptotics at the number of atoms in the universe. Coppersmith-Vinograd is one of them. So not exactly practical. So to add to the academic discussion, Jim Demmel, myself, and Olga Holtz, we showed, actually, and Bobby Kleinberg, I'm sorry, I forgot to mention him. Bobby Kleinberg was part of this. We showed that it doesn't matter what the matrix multiplication exponent is. If there's an algorithm to achieve it, then it can be achieved stably and for a certain logarithmic definition of stability, which I'm kind of like burying under the rug, meaning that you will have to extend your number of bits, because the error that you're going to get is going to be polynomially multiplicating epsilon machine, and so you'll have to extend your epsilon, the number of bits that you're willing to take to accommodate for that. So that was Jim, Olga, Bobby, and myself. And then with just Jim and Olga, we did that. We showed that QR, so the QR factorization can be obtained in the same complexity, with the same complexity. And therefore, you can do quite a bit more. You can do SVD, you can do Eig, you can do inverses. But for this kind of stability, for this kind of definition of stability. And the key tool is always, as it has been, the block matrix multiplication, which is what leads to being able to talk about the complexity of matrix multiplication to begin with. Okay. Again, this is a purely theoretical result, given that we don't know what the algorithms may look like. And since the best algorithm that we know for doing this is galactic. So it's unlike Strassen. So again, I want to stress the fact that Strassen is not of this type, that it starts achieving its potential for fairly small matrix sizes. Okay, but what can be taken away from this? In particular, any algorithm based on matrix multiplication and QR can be achieved stably in this sense of the logarithmic definition, and with computable complexity in terms of the complexity of matrix multiplication. So most of linear algebra in this sense has the same complexity as matrix multiplication. And the good thing about these kinds of algorithms is that they're highly parallelizable. So obviously, as soon as you use block matrices, you introduce that possibility. Okay, now, if we go back to the discussion that we had this morning, in particular, if you remember the randomized rangefinder / SVD proto algorithm, in which all you do is essentially you take a matrix, you multiply a random matrix to its right, and then you do QR. It's matrix multiplication and QR. These kinds of proto algorithms can be achieved in the same complexity as matrix multiplication, I mean, with pseudo random bits. So that's another issue that we're kind of sweeping under the rug. Of course, we're always acting as if these random number generators were actually producing random numbers, not pseudo random numbers. But we have to work with what we're given. So that's the takeaway. Because of all of this theory, this kind of randomized rangefinder algorithm has this extra benefit, that it can be done faster than with classical methods. Okay, so that's one of the issues for which randomized algorithms are known to be better, or to be more versatile, I guess, than classical linear algebra algorithms. But now let me talk about another issue, and that's communication. So far, we've only, or mostly, or almost only, discussed arithmetic and the blockable quality of algorithms, and the fact that algorithms can be parallelized. So these are costs that are incurred only if matrices fit in the fast memory, CPU cache. Okay, because we've ignored any kind of transport, latency, bandwidth, and so on. So we're going to now bring them back, or rather, we're going to bring them to the forefront. It is not unusual at all to have to operate with matrices, with humongous, with enormous, with gigantic, with galactic sort of matrix sizes that will not fit in the fast memory. So in that case, there's an additional cost that is incurred in all of these computations. And that is the time that's going to be spent around passing messages. Okay, in the sequential case between the slow memory and the fast one, and in the case of multiple processors over a network, then passing around of information. Okay, so communication becomes a cost that has to be factored in. And so, for these very large matrices, there are costs of multiple types, and they come actually with three components. There's the arithmetic cost, which is the number of floating point operations times the time per flop. There's the number of words moved over the bandwidth. And then there's the number of messages passed around times the latency. And these last two represent communication costs. Okay? There's the arithmetic, which is what we've talked up until now. And now we're also talking about these communication costs. Why is this even relevant? Well, it is very relevant because on modern hardware, it turns out the rate at which the cost of doing a flop decays, which is much faster than the inverse rate of the bandwidth growth, which in turn is much faster than the drop in the latency. So these things do not happen all together. The gaps, in fact, are growing exponentially in time. And here's a table that is perhaps a few years out of date, and I apologize for that. But the annual improvements a few years ago used to be like this. So the time per flop would improve by 59% every year, roughly. But the bandwidth and the latency lagged far behind. So basically every year, the communication costs gain over arithmetic. Every year. So let's take a look at what this means on a concrete example. So for the naive matrix multiply algorithm, where you have two large matrices, they cannot be brought, they cannot fit in the fast memory. So what you do instead is you store them on the slow memory, and you bring up one row and one column at a time, and you do your computation in the fast memory, and you go and write down the result. Okay. So it turns out that the number of reads and writes for that is n cubed plus 3n squared. And the arithmetic cost is 2n cubed. So you see they have the same order. But the constant that this is going to get multiplied by is growing every year, relatively to the constant that this is going to be multiplied by. And so communication is becoming more and more the lion's chunk, the lion's share of this complexity, the runtime of an algorithm. It dominates. Now, if instead you consider block matrix multiply with blocks of size b by b, then you will reduce that by a factor of b over 2. That's how many you're going to get. And if, moreover, you make your blocks really big so that only 3 of them can fit in the fast memory, then the costs become omega of n cubed over square root of m, where m is the size of the fast memory. So what does this mean? It means that this represents a significant, a huge reduction in communication costs. Okay? Block matrix algorithms are excellent for reducing communication costs. Okay, so how much can you reduce the communication costs with this strategy? Well, in a paper that I think won some SIAG, so SIAM linear algebra group prize in 2012, Baller, Demelholtz, and Schwartz showed that this is optimal. You can't do better than this. So by doing block matrix multiplication, you achieve the optimal amount, optimal in the sense, the minimal amount of communication when the matrix size is huge. And later on, they could show that the same thing happens for QR. Okay? So this is important. Block operations are key. Okay, so what does this mean? It means that it might behoove you to consider trading arithmetic for communication. So for the sake of being able to bring into the fast memory these big blocks of matrices and operate with them at that level, and then doing a minimal amount of communication by writing the results on the slow memory, you might be willing to trade some arithmetic to be able to do that, because that reduction of square root of m, where m is the size of the memory, is huge. Okay, so this talks about a need to restructure linear algebra computations, numerical linear algebra computations, with this minimization of communication in mind. It turns out that the lower bounds that they proved in 2012, they hold for all laws, for all, so basic linear algebra subroutines, for LU, for QR, for IGSVD, and tensor contractions, and every year or so they come up with other things for which it holds. So there are computable, minimal amounts of communication that you need to do. And a lot of the time, using only or mostly matrix multiplication and QR in an algorithm will take you there. It's desirable because it will take you there. Okay, so here's one question that I'm going to answer next. I'm going to give you a 5-minute break and then we'll come back. Can we organize eigenvalue algorithms to achieve optimality of communication in this sense? I think I'm going to go back and remind you of the fact that we're talking about whether or not eigenvalue algorithms can be reorganized, can be rewritten with this idea of minimizing communication and achieving optimality in mind. So here's one example. This is a divide and conquer algorithm for the eigenvalue computation, which I will refer to perhaps in a slightly unfortunate name that I only realized before I wrote it down, as a DNC. Okay, so the idea is as follows. You want to count how many eigenvalues you have in smaller and smaller regions of the plane. Okay, so you want to localize these eigenvalues. The closer you can localize them, the better you're going to know them in some sense. So you want to break up the problem or the matrix into two smaller subproblems. One of them containing having all the eigenvalues inside or outside a disk or equivalently to the left or to the right of a line. So why is a disk equivalent to a line? The answer is because of Mobius transformations. Okay? So Mobius transformations are these simple transformations that can map the plane onto itself such that if you have a line, the left and the right get mapped on the inside and respectively the outside, or vice versa, depending on how you want to do this mapping of the line. And these Mobius transformations are essentially very simple fractional transformations of the plane. And this sort of issue is, or this sort of transformation is very easily to write. It's very easy to write in terms of a matrix. So you can do this. So once you do this, once you decide, you have your matrix, you decide, okay, so I break it up into two parts. One matrix of smaller dimension that has all the eigenvalues inside the unit disk, one matrix of smaller dimension that has all the eigenvalues outside a unit disk. And then you recur. You can recur until the problems are small, for example, fit into the fast memory. This is the spectral divide and conquer. This sort of thinking applies to a variety of problems which are all more or less equivalent and can all be solved by looking at regular matrix pencils. So what are pencils? Pencils are pairs of matrices correspond to the generalized eigenvalue problem, which says, which I'll define actually more carefully on the next slide. Eigenvalue problems will correspond to one of these two matrices being the identity, B being the identity. So they're a particular case of pencils, either symmetric or non-symmetric. And of course, if you can solve the symmetric eigenvalue problem, then you can do the SVD. Notably, this divide and conquer algorithm, it will compute the generalized Schur or Schur form, or it will do the full decomposition because the generalized Schur form is just diagonal for symmetric matrices and the SVD. Okay, And the key fact here, where's the random part, right? The random part is in the fact that to count eigenvalues on either side of the barrier, you have to rely on a randomized rank revealing decomposition. So you'll have to define eigenvalues on one side of the barrier as being 0, on the other side as being something else, and then you look at the rank of the ensuing matrix. It's not going to be exactly 0, it's not going to be exactly something else, but you look at the rank of the ensuing matrix and you can say, okay, so this is how many I have. That's why the rank revealing. Okay, so in 2011, with Gray Ballard and Jim Demo, we offered a general outline, which we call the high-level strategy, on how to do this using a randomized rank revealing decomposition. So again, roughly sketched, we look at the unit disk, we decide how many eigenvalues are inside. How can we use that information? Well, if you were to do repeated squaring of the matrix, that would drive all of the eigenvalues inside the unit disk to 0, and all the ones outside to infinity. So that would create a huge gap. Then you could look at the matrix, do a rank revealing decomposition, and decide what the rank is, and therefore how many are inside. Because the ones that are inside are going to correspond to those eigenvalues that are close to 0. And then you recur. But there are some issues with this on the face of it. One of them, the simplest one, being that repeated squaring is not stable. Okay, you're talking about raising a matrix to very high powers. That's not exactly what you want to do. The other issue is, as I mentioned before this morning, is that deterministic rank revealing factorizations are too complex to analyze or to show to be optimal for communication. The guess is that they're not. And the third one is, how do we count eigenvalues? So, okay, so you have the rank revealing factorization. What do you do to figure out how many eigenvalues you have? How do you break this up, in other words? We'll see in a moment what that means. These are some of the issues. Okay, so before I go on, I tell you how to resolve them. Let me tell you a little bit of the history of divide and conquer. So these ideas have been around for a long time, certainly since the advent of the PRISM project in the early 90s. But then one approach to counting eigenvalues has been to use the sign function. And this was studied in the early 80s by Howland and Roberts. And basically, to compute the sign function, which basically what it does is it gives you a decomposition of the matrix in which you have V, which is the set of eigenvectors, times pluses and minuses on the diagonal corresponding to eigenvalues that are positive and negative, times V inverse. That's the sign decomposition. And it can be computed using Newton iterations, and it involves taking inverses. Another approach, which is inverse-free, was pioneered by Bulgakov, Godunov, Malishev in the late 80s and early 90s, and then later led to a pretty important paper by Bai, Demel, and Gu in 97, which was the basis for our high-level for constructing the RU-RV decomposition, and for our high-level strategy for computing eigenvalues in 2011. Since then, better approaches have been devised for the symmetric eigenvalue problem. And the first one of which was by Eugenia Katsukasa, who's going to talk in the conference here, and Nick Hayam in 2013. But roughly speaking, divide and conquer remains probably the most competitive algorithm for a candidate to communication optimality. And I'm going to tell you a little bit why inverse-free has been our choice algorithm. Partly because in general, inverses are buggier. Taking inverses is buggier than for example, doing QR. So it's less desirable in a certain sense. Okay, but this approach, the sign function approach, has been used by Banks, Garza Vargas, Kulkarni, and Srivastava. I think the paper was put up in 2020. I couldn't remember exactly. I know that it's gone through several revisions and so on. Right now it says 2022, but it's been out for 2 years. So I want to give credit where credit is due. For a smooth analysis version of solving this non-symmetric eigenvalue problem, which achieves near matrix multiplication time. So DNC with a sign function. Okay, so let's go back to the issues that I mentioned. The first one was repeated squaring. How do we settle repeated squaring? Well, instead of repeated squaring, we're going to do implicit repeated squaring. And it turns out that if you do it implicitly, it's stable. We will use a randomized rank revealing factorization, which I've been mentioning, which is very simple and very much alike the rangefinder algorithms that I mentioned in the first half of the talk. And then one can either count the eigenvalues using the sign function or do something else. But let me tell you a little bit, not about the non-symmetric eigenvalue problem, but about the generalized eigenvalue problem, which is bigger in some sense. So you can think of it as, I mean, it has it in the name, it's just the generalized eigenvalue problem. So if you have two square matrices, you can define an eigenpair to satisfy this relationship. So lambda v, a minus lambda bv is equal to 0. V cannot, of course, being an eigenvector, it cannot be allowed to be identically 0. When B is the identity, you can recover the one matrix eigenvalue problem. Now, clearly, to have something like this, you've got to have that the determinant of A minus lambda B is 0. And the determinant of A minus lambda B, when you think of lambda as a unknown, is a polynomial in lambda of degree at most n. When this polynomial is not identically 0, we call the pencil regular. Okay, so that's the definition of a regular pencil. When can this fail? When can the determinant of A minus lambda B be identically 0? And what does this even mean? Well, for example, if A and B have non-trivial null spaces that intersect, then actually the entire complex plane is in the spectrum, because you will have a non-zero vector for which will be an eigenvector for any lambda in the plane. Essentially, that's what it is. And when B is singular, you'll have an eigenvalue at infinity, because the essentially because the top coefficient of this determinant of A minus lambda B is going to be 0. So these are examples. These are not the only examples when the determinant of A minus lambda B fails to be not identically 0. That sounds strange. But in general, we will be interested in regular pencils, which say that this pencil has bona fide eigenvalues. It has a finite number of eigenvalues. They're all finite. Okay, so again, the summary for divide and conquer is to pick a line or the unit disk equivalent via Mobius transformations, drive the eigenvalues on either side to 0, respectively, infinity. We'll see that this infinity actually will become 1, because we're not going to look at, we're going to change the problem a little bit so that, you know, you have eigenvalues going to 0 and 1 as opposed to 0 and infinity. Through this implicit repeated squaring, which I haven't yet defined, but I will do so momentarily. Then use this rank revealing factorization to split the problem into two smaller ones and then recur. Is it recur or recurse, or does it matter which community you come from? I don't know. Okay, so let me talk to you about this implicit repeated squaring. So the Bai-Damolgu paper from 1994 constructed an algorithm for approximating the projectors, the projecting transformations, P of right z greater than 1 and left z less than 1. These are projectors onto the spaces determined by the eigenvalues that are outside and respectively inside the unit disk. And the algorithm is very simple. And it is essentially based on matrix multiplication and QR. So you start out with A0 being A and B0 being B. And then you set up your A's and B's like this, and you do QR on this tall matrix. And you assemble your next iterates, Bj plus 1 and Aj plus 1, in the following way. So Bj plus 1 is going to be this block, take the Hermitian transpose times Bj, and Aj plus 1 is going to be this block, take the Hermitian transpose times Aj. And you repeat this until convergence. Convergence is defined in multiple ways. You can pick your own definition of convergence. You just want to get to the point where there isn't significant change. Okay, two things to note when we talk about implicit repeated squaring. First is that if you look at A minus lambda B, when B is non-singular, the eigenvalues of the pencil are those of B inverse A. Okay? And you might ask, why not just deal with it as if it were a matrix? And the answer is because of B inverse. That's an inverse that we're trying to avoid taking. We want to not take inverses. But knowing that, let's see what it means that we're doing implicit repeated squaring. First, if you do QR, then you can bring the Hermitian transpose on the other side, and you Q star times your matrix is equal to the R factor. So this is what we do here. And note that since this is identically 0, that means that the second batch times the column will give you 0. So in particular, that means Q12 star of AJ is Q22 star BJ. So now what that means is that if you bring BJ inverse onto the other side and multiply Q12 on this side, you get this. Okay. So now let's look at what happens to B inverse J plus 1, AJ plus 1. This is just the definition. Okay, this is how we define BJ plus 1 and BJ, AJ plus 1 and AJ. And now I've just, excuse me, I've just argued right here that this quantity Q12, Q22 star is actually AJ, BJ inverse. So let's swap it. And what do we get? We get BJ plus 1 inverse AJ plus 1 is actually BJ inverse AJ squared. So this is the implicit repeated squaring. What this says, oh, sorry. What this says is that if you look at this matrix here, AP plus BP, which are your converged, or actually it's not even converged, it's the pth iterates in this implicit repeated squaring algorithm. So AP plus BP inverse BP, which you rewrite as such. Well, this is the identity plus B inverse A to the power 2 to the P, and take the inverse. And this latter matrix approaches the projector, because essentially what happens is, like I said, so you're taking the eigenvalues of B inverse A, those that are inside get shrunk to 0, those that are outside go to infinity. So if you look at taking the inverse, now the ones that are outside are shrinking to 0, and the ones that are inside become 1. I guess that's more or less what I'm trying to say. Yes. So this becomes a projector. And by them, we'll go also calculated how many iterations, how big P will have to be needed in terms of the distance of the spectrum from the unit circle. If you want a certain tolerance, how many iterations do you have to do? Of course, because it's implicit repeated squaring, it's not too many. You're going to have to take essentially logarithmically many. But it's not logarithmically in the size of the problem, but there are other quantities that are involved. Okay, so basically this is a very, very simple algorithm based on matrix multiplication and QR, which after this implicit repeated squaring gives you a new pencil for which the eigenvalues have been driven to 0 and 1. So we can now do, because the gap between the eigenvalues that lie inside and the eigenvalues that lie outside, and I think I did it the other way around, I should try and not gesture as much, sometimes meaningless. The gap is wide. So we can use a randomized rank revealing factorization to split the matrix. So here's our URV, which I've mentioned a lot, but haven't actually shown you. You take a matrix as your input, and then you draw a randomized Gaussian matrix B of the same size. You obtain a Haar n by n unitary or orthogonal matrix, V, as the Q factor in QR of B. And then you do QR on A, V star. So what have we done? We have scrambled the columns of A using a unitary or orthogonal matrix, and we do QR to it. So we're basically trying to reveal the rank of A. That's what this does. Now, we've done this before, but not with full n by n matrices. We've used Gaussian matrices with much fewer columns than the number of rows. And I'll explain in a moment why we don't want to do that now. The output of this algorithm is URV such that A is equal to U times R times V. So this is the randomized rank revealing factorization. Of course, this should be familiar because it's the same thing that we talked about in part 2. The difference, like I said, is that now we use a whole random matrix. Why are we doing this? In some sense, when you do divide and conquer, you don't want to split 1 or 2 or 10 eigenvalues. The gains come when you split a whole chunk of them. Okay? You want to split as close to half as you can, because that's how divide and conquer works. A fraction, a significant fraction will do. So what does that mean? It means that these eigenvalues that are driven to 0 and which will have to be recognized by this rank revealing factorization constitute a fraction of the total number of eigenvalues. So before we were thinking that it was just a few, now we're thinking it's a fraction of them. Before we were concerned with saving complexity, we were saying, okay, so I want to have an algorithm that's proportional not to n, but to the number of eigenvalues that are non-zero, sorry, singular values that are non-zero. But now that itself is proportional to n. So we're not concerned about complexity anymore. We're going to use the whole matrix. Okay, so I've said all of this, and we want to ensure accuracy. We want to compute things as accurately as possible, and that's what we need to do. Okay, well, and it turns out that if you analyze this RURV, it turns out that it is a strong rank revealing factorization in the sense of Gaussian-Stat 96, which is the epitome, the pinnacle of deterministic rank revealing factorizations. In the sense that it really approximates the singular values of A well, okay, it's all relative, of course, but this is the requirement. It approximates, the singular values of R11 approximate those of A, and the singular values of R22 approximate those, I apologize. I'm starting to fade away. The singular values of R11 approximate the biggest singular values of A, and those of R22 approximate the smaller ones of A. And this is the ratio by which you can be off. And of course, since now we know that the matrix will approach a projector, that means that some of the singular values will be very close to zero, as close to zero as we want them. And so we'll have a big gap here, and there's room for this rank-revealing factorization to be very good. Okay, so using the results of the smallest singular value bounds for a Haar corner, you can show that with probability as good as you want, essentially, you can do this rank revealing factorization fast, and it's as good as the best deterministic RQR, and it's also communication optimal because it only uses matrix multiplication and QR, and those can be computed with minimum amount of communication. The important thing about this RURV is that it generalizes almost immediately to products of matrices and their inverses without actually computing the product. So if you want to apply this rank revealing factorization to something like B inverse A without computing B inverse A, because we don't want to take inverses, you can. You only have to generate one random matrix and you can do it. So it works for a pencil, not just for a single matrix. This overcomes a big assumption in the paper by Baidem and Gu, which used column pivoting to produce a randomized, to produce a deterministic rank revealing factorization that only depended on B. So, it was unlikely to work on the face of it. But now with this randomization, we can show that it will work regardless of A and B. Okay, so after obtaining this RURV, you can obtain accurate approximations for the left eigenspace and the right eigenspace via this implicit repeated squaring and generalized RURV. And you can build two matrices here, QL star AQR and QL star BQR, which look almost block triangular. So we expect that E21 and F21 are going to be small. A priori, you don't know how to choose these blocks, but you can, for example, choose to minimize their the ratio of their one norms. And this tells you how to split your problem. So basically now you split the pencil problem into A11, B11, and A22, B22. And that's the divide and conquer. Okay, it can fail. So failure can occur, and it occurs with small probability. And if it fails because of the matrix chosen in RURV. But you can catch the failure because it will fail to split well. Okay, so if you split, then by definition you've obtained a rank revealing factorization. If you can't split, then you can't. In the tiny chance that you fail to split, you can repeat. You can pick a new matrix V, random matrix V, and repeat the algorithm. Okay, so now I'm reaching the very last part of my talk, which is appropriate because I think I should be finishing soon. And let me talk about how to use this to do a randomized eigenvalue decomposition, approximate randomized eigenvalue decomposition by adding a little randomness at a time. So in around 2020, Banks, Vargas, Kulkarni, and Srinivasa came up with a wonderful theoretical computer science algorithm to approximately solve the diagonalization problem. It had all sorts of nice properties. But instead of forward stability, which means you compute your eigenvalues and eigenvectors and you want to argue that the accuracy with which you computed them is good. Instead of doing that, we're going to do what is known as essentially backward stability, which means we're going to solve a nearby, and by nearby, I mean randomly perturbed problem. So in philosophical terms, this falls squarely within the realm of smooth analysis, which is something that I mentioned in the first part of my talk. Essentially says, if you don't know how to solve your problem, add a little bit of a tiny little randomness to it. It'll take you off the edge of the singularity, and now you can do your algorithm and it'll work, provably work. So that's what they did. They took the matrix A and they added a little bit of perturbation to it in the form of a Gaussian IID Gaussian matrix. Now, what does that do? Is it creates an eigenvalue gap and it controls the eigenvector condition number. Okay, so the worst problems, our worst eigenvalue problems that you have to solve are those where you have eigenvalues that are too close together or where the eigenvectors are almost parallel. And by adding this tiny little bit of perturbation, you get away from that. Now, that doesn't mean that the eigenvalue gap is good or the eigenvector condition number is good. They're polynomial in the size of the matrix, but they're controllable. And this is the most important thing. And then you can compute accurately the eigenvalues and eigenvectors of the perturbed matrix, or again, in the sense of backward stability, which means that there's a matrix nearby this perturbed matrix for which you compute the eigenvalues and eigenvectors correctly. Okay, and to do so, they had to do one very important thing, which was to figure out how to shatter is their term, the pseudospectrum of the matrix. What's the pseudospectrum of a matrix? Well, it's the set of all numbers that are eigenvalues for a slightly perturbed problem. That's what this is. So that's the pseudospectrum of a matrix. The epsilon pseudospectrum of a matrix is the set of all values that are complex, such that this value is an eigenvalue for the slightly perturbed matrix. And there's a problem involving this pseudospectrum in our divide and conquer ideas, which is that if you choose a line or a disk that crosses the pseudospectrum, you cannot do the partitioning, okay, because you don't know what you hit. So to correctly split the spectrum, you have to pick a line or a circle that does not intersect the pseudospectrum. And so this split the pseudospectrum into parts becomes very important in that context. What does it mean to split or shatter the pseudospectrum? Basically, it says you have to figure out how small epsilon will have to be so that this perturbed matrix A tilde, at that point, the spectrum looks like a union of balls. Okay? If the matrix that you start out with has distinct eigenvalues, then if epsilon is small enough, the pseudospectrum is just a union of balls. At some point, as epsilon grows, these balls coalesce. And when they do, the eigenvalues start moving around and shifting. So it becomes difficult to characterize, to know what's going on. But if you can figure out how small epsilon has to be so that your pseudospectrum is actually just a bunch of balls, then that means that you can pick, you know how to choose lines to split it, essentially. So that's why this is extremely important to know. And the answer to this question was shown by Banks et al. To be inversely polynomial in that. The power, I forget what the power is. It's not very small. It's something like, was it 7.5? I forget. I don't remember. Yeah. Sorry. Yeah. So it's a constant. It's not tiny, but it's a constant. Okay, so going back to the divide and conquer, you have to construct a grid separating the eigenvalues so that the pseudospectrum for this epsilon machine, which is very small, will be entirely contained within the cells of the grid. And then you can take one of the grid lines for your splitting line. You can say, okay, so since there's no intersection of the pseudospectrum with the grid and every single eigenvalue is contained within a cell, we can just pick a line in the grid to do the split. It turns out that there are lines that will split this pseudospectrum well, in the sense that they leave a big chunk of eigenvalues on either side. And then you can use the sine function to tell how many eigenvalues there are on each side of the line. This involves calculating inverses as part of the Newton iteration. You can shift that by the identity and use RURV to construct the rank revealing factorization, which then gives you the projectors onto the left and right subspaces. And now at this point, you've split the problem into two and you can iterate. I'm not going to go into much more detail than that. But this algorithm for eigenvalues is absolutely remarkable because, first of all, it shows that it's achievable in matrix multiplication complexity, perhaps polylogarithmically more. But again, the matrix complexity is perhaps not thought of being exactly 2, but 2 plus epsilon. Polylogarithms would very nicely be swallowed into that. It is logarithmically stable, given some number of bits that is, some machine epsilon, which is inversely polynomial. So some number of bits that is logarithmic in that. Then it uses, and very smartly so, many of the results we mentioned before. And it's a true tour de force in showing convergence in finite arithmetic. I'm in awe at the amount of work and precision and sophistication that's been required to do this. Okay, so it blends random matrix theory, theoretical computer science, and numerical linear algebra in a very sophisticated way. Okay, so inspired by that, with Brian Schneider, whose poster will be, if it's not already out there, it is already out there, okay, on this work. And with Jim Demmel, we worked on the generalized pencil problem, A minus lambda B. And let me tell you a little bit about it. So for a regular pencil, especially for a perturbed one, this perturbed B tilde will be non-singular. So in theory, the spectrum will be the same as for B tilde inverse A tilde, and yet we don't choose to see this as a single matrix problem. And the reason for that is that the pseudospectra for the pencil and for the single matrix B inverse A look very different. And Ryan has pictures that demonstrate this. You should go and see his poster. Small perturbations in A and B, which you are likely to get. If you get A and B, you will get them modulo small perturbations. But that's not the same as saying that you'll have small perturbations in B inverse A. So even though in many cases, people have chosen to identify the pseudospectrum of the pencil with the pseudospectrum of B inverse A, and for example, spectra and pseudospectra, the seminal, the Bible, I guess, of the textbooks on the subject, chooses to do so. We felt that it's better, more natural to keep the perturbations into the matrices themselves. So to do that, you have to avoid taking inverses, and so stick to the Ballard, Demmel, and Dumitriu algorithm from 2012. We cannot use the sine function, but we can use the implicit repeated squaring instead. So again, what's the pseudospectrum of a pencil? It's this quantity, it's the set of values in C for which there are small perturbative matrices delta I and delta B, such that lambda is an eigenvalue of the perturbed pencil. Okay. And we've showed so far that we can shatter the pseudospectrum of the perturbed pencil. Once again, epsilon will have to be inverse polynomial in N. a higher power than for the single matrix case, but it can be done. Sorry. Oops. Okay. And we have also shown that the algorithm is accurate and exact arithmetic, and we're working on the finite precision. So if you want to understand more about this, go and talk to Ryan at the poster session. Okay, and I've blathered on sufficiently, so here are my conclusions. I would hope that by now it's clear, even though obviously the fact that you're at this conference tells me that you're most likely already convinced of it, that random matrix theory and numerical linear algebra intersect and enhance each other, and that produce beautiful methods and tools that can then be used by sciences, by engineering, by signal processing, data science, and so on. The issues that randomization can help with are bevy: complexity, theoretical guarantees, communication. So to optimize, you might want to randomize. And if you don't know how to solve it, maybe jiggle it a little bit. Thank you very much.